High school calculus, infinitesimally small numbers and derivatives. Well, this is the beginning of calculus. If you already studied the algebra 2 and are familiar with function, then you can move on. Now, we try to cover entire derivative section. As you know, there are several sections in calculus: derivatives, integrals, infinite series, and others. Okay, so the single video is very aggressive. Try to give you entire derivative sections, but instead of going to the details you can do practice by yourself. We try to teach something missing in the math textbook, and because they are missing, a lot of us high school students feel calculus is difficult, confusing, and they don't like it. Okay, so we know exactly what is missing. What you need to learn before you go into the calculus is that the fact that calculus uses a new type of number. Okay, new type of number is based on the concept of infinity. And so far you learned many different numbers, right? Started with integer, rational number, you keep expanding it, right? Irrational number, so and so. Okay, and beginning of algebra, if you listen to our video, you know the new number called unknown value. And that is a number, but we don't know the value, but we treat it as a number, and we develop the algebra. So it's not really emphasizing, it's not overstating to say that algebra is based on this new number, unknown value. The same way you can say that calculus is based on this number called infinitesimally small number. Okay, so here's a question. We have a real number, right? The real number is like 3, 2, 0, or square root of 2, or whatever, pi, e. Those are real number. The real number has a fixed value, and so far in algebra, unknown value is also has a fixed value. Okay, now we deal with a number that doesn't have a fixed value. How we define that? You say, okay, my number 1 plus, we write 1 plus, is the number, it's infinitely close to 1, but it's not 1, just infinitely close on the positive side. If negative side, we write 1 minus. Okay, it's infinitely close to 1, but it's not 1. So what kind of number is that? Okay, if you do subtraction, 1 plus minus 1, there is some amount very close to 0, but it's not 0. Okay, so there's no fixed value. That's the new number we need to introduce in order to construct the entire calculus theory. Okay, 0 plus is called infinitesimally small number. If you do the 1 minus 1 negative, it's going to be 0 plus. But if you do this number minus 1, then it's going to be infinitesimally small negative number, right? So we know infinitely close to 0, but it's not 0. So what is it? Well, I said that infinitely close to 0. Can you give me a fixed value? No, I can't. The number we define here is the kind of number just has the adjective infinitely close number. It doesn't have a fixed value, okay? And this is important concept in the calculus. Once you get that, nothing difficult about the calculus. So, in order to handle that kind of number, how do we deal with that kind of number? So there are some mathematic notation we have to define called the limit, okay? N is equal to infinite and 1 over 10 nth, so 0.1 plus 0.01 plus 0.001 plus so on, so it's going to be 0.1111, right? This one we can write it 1 over 9. This has a fixed value, right? And n goes to infinity. That means we write this way: n goes to infinity, and put the n here. So this notation, math notation here, limit n goes to infinity means make n goes to infinite. Okay? So that's the meaning of limit. So limit means the final destination value. Okay? So if you say limit 3 plus goes to 3, well, if you have a negative limit 5 negative is 5, because infinitely close to 5 from negative side. But if you say limit, where is limit? 5. Say this is a 5. And my number 5 minus is here, no, here, no, here, no, here, no. Infinitely close to 5. The limit means, so if you go all the way infinite path, where does it go? It goes to 5. So final destination value is a limit. That's how you understand the limit. Okay? So we have infinity, the new notation. This is infinity. We can write a negative infinity, or number infinitely close to a but larger, or a negative is infinitely close to a but smaller. Okay? Can we add, subtract, multiply this kind of number? Let's try. Operation of infinity. Infinity plus infinity is infinity, right? Yeah. Infinity plus negative infinity. We don't know which infinity is bigger, so unknown. Infinity minus infinity, we don't know. Infinity negative minus infinity will be infinity. So far so good. Infinity times infinity is infinity. Infinity times negative infinity is negative infinity. Infinity divide by infinity? We don't know, right? Because we don't know which infinity is bigger. Now, infinity plus a, you have to go through this. Infinity times a, infinity divided by a, no matter how you divide, infinity is infinity. If you divide a by infinity, is 0. So what you do is, using limit, this what it means is limit n goes infinity and a over n. N goes infinity, then it's 0. Okay? Operation of infinity continue. In the function, so what's happened? Let's look at this function. Here, you know, black dot, that include this point. White dot is excluded. So this line is defined up to where? Tell me where. There's no fixed point. Correct? Okay, so this function is defined up to 0 plus. Okay? Well, this is the infinitesimally small number. The range of this function is defined here. But here's a black point. So this function, the range is negative infinity to 0. Okay? So if you say f negative 1, which is here, then it's 1. Okay? f0 negative, infinitesimally small number, negative number, it's going to be 0 plus. So if f is 0, sure, it's a definite value. Okay? If f is 0 plus, that means this guy. Then y is 1 plus, not 1, okay? 1 plus. And f is 1, then it's a definite 2. You follow? Okay. So this function is defined up to 0 plus. And when function x is 0, y is 2. This function defined up to 0 negative. Okay, so minus 1 is going to be negative 1, right? 0 negative means here. Then it's going to be 0 negative. 0 is 2, definite value here. Okay? 0 plus is 1 plus, and 1 is definite value 2. 1 is 2. You see, we deal with the infinitesimal number and definite number all together. So we need a precise definition of function here. For example, the function like that, let's look at negative 1. Negative 1. This is wrong. 1 negative. Here. Okay? Then it goes negative infinity. 1 positive here goes positive infinity, this one. And 2 negative here goes to infinite, and 2 positive here goes. So what you do is, for example, what is f1 negative is limit n equals 0 and x is gonna be 1 minus n. Oh, n can be 0 or infinity, whichever, right? Plus minus 3n 1n minus n plus 2 over negative 2. Okay, so this become infinitely small. You expand this equation and put the n equals 0. What's left? The bottom is going to be 0 positive. So this whole thing's, the limit value is going to be negative infinity. Okay, so let's practice the how you find limit. Say limit 0 plus 0 negative. The 0 negative you limit, the final value is what? 0 here, right? 0 positive, the limit is the final value, so it's going to be 1. Once you say limit, you take the value all the way, so you can get the definite value. Okay, don't get confused here. Limit 0 negative means here 0 negative, but you take a limit all the way, so this value, so it's going to be 0. Limit 0 positive, you take all the way to 0, then it's going to be 1. Okay, and the limit 0 doesn't do anything, it's just plug in 0, which is 2, this one. Okay, so this is a limit. We did this up there, same thing. The meaning of limit is you bring this infinitely close value all the way to the end. What is the end value? So limit always give you the definite number, no more something positive or something negative. Okay, let's practice this. You practice this, find the limit. What you do is you rewrite it this way: limit n equal infinite, and replace x with n. So the n goes infinite means 1 over x goes to 0. So that's where you understand which way it goes. Okay, but answer is always definite number after limit. Okay, now we have an important series related to this infinitesimally small numbers stuff, but we skip this part. Okay, now since we talk about infinitesimally small number, when you take a ratio, what's happened we don't know, right? But let's use a limit method to figure out. Okay, when you take the infinitesimally small number divided by infinitesimally small number, what's happened? unknown unless you figure out limit n equals infinity method, this function. Okay? And for example, here's the example. If you make x is 0 go to 0, sine over x is going to be 1. This is a very important result. And the proof of this is a little bit complicated. But if you do x square at the bottom, then become infinity. So this sometimes goes infinity or negative infinity, or goes to 0, or goes to some definite number. That depends. Okay? So we deal with this. We have another infinity minus infinity, and infinity infinity over infinity. This is same as 0 positive over 0 positive. Okay, infinity divided by infinity is almost same as 0 positive over 0 positive. Okay, so this infinitesimally small number, the ratio, we need to investigate more what this is about. Okay, now here's some more limit result. Okay, so when x goes to 0, this goes to 0, so it's a square over x. This is a 0 divided by 0, right? But if you expand this, a square plus 2ax plus x square minus a square, this goes out, and we divide by x, so 2a plus x. Now actually, if you work out, x goes to 0, this goes to 2a. You know what I mean? Oh, here the answer. Okay, so if you work out, you can find the ratio, definite value of the ratio. Okay, try this and try this one. If it's tough, you can find a simpler question in the math textbook and try it out. So here point is, or could be negative, whichever, this ratio, if you examine the limit, it could be something definite value. Is that important? What's the use of this? Why are we doing this? This is exactly the definition of the derivative. So I show you why this is so important. Okay, in algebra section, you learn that Euclid geometry, there are postulate, and that doesn't cover the arbitrary curve, like, you know, quadratic equation has a curve, right? And the line can contact single point, and this single point is at the 1, or it could be 2. What's happened? If you move the parallel line, then you are intersecting 2, eventually become a single point, then eventually no contact at all if you move the parallel line. Okay, so there seems to be a single point contact. You can tell single point contact if you move this line keeping it parallel. Okay, what does it mean? This is single point contact. The linear equation of this is slope. So we define the slope of this curve by line that is contacting at the single point. So if you get this ax plus b, this a is the slope at that contacting point, because its curve, the slope keep changing, right? So how do you define the slope of the curved line? Well, you find the line, linear line, that contacting at the single point, and that's define the slope. Okay, so in order to do that, we have to handle the simpler function, because if function is like this, right, then slope is like this and slope is like this. So from here, slope is gradually changing and suddenly jump. So slope is going to be gradually increasing almost from 0, then suddenly become negative and gradually increasing again. So the slope function of this kind of function, it's not continuous, is going to cause some discontinuity. Okay, so we deal with only continuous function here. Is a continuous good enough? How about this kind? The function is continuous but has a kink like this. Then again, if you try to figure out slope probably here 0, increasing, and suddenly boom, negative. So again, slope function of this is like, from here it's increasing and go negative and start increasing again, right? So slope function is going to be complicated function. So in order to avoid this, we say function must be smooth. Okay, so we will handle only simple function, but most of them we learn in algebra 2s are continuous and smooth, except for like a tangent. Tangent has a bunch of discontinuity here, and some rational function has discontinuity, but within this range it's smooth and continuous, so we can deal with it. Okay, so we consider the slope function of a function. How we determine the slope function? Here's how. We use derivatives. So derivatives is like, okay, suppose the function is the curve. Okay, then here's x. What is the slope at the x? We need to find this line. So what we do is the slope of this point is linear equation. We take next point, then slope is going to be like this. So it's going to be y, and this y plus delta y, right? So slope can be approximated by dy delta x delta y delta x. Now we use the limit delta x 0. So if you take a limit, then we are moving this toward x infinitely close. At the final point, we get a definite number, and that number we call dy dx. Why we call that? Because this is a slope function, slope value of the original function. Okay, so this is the definition of derivative. So we take a very close value of x and calculate y, which is y plus delta y, and take the ratio. The delta y and delta x both are infinitesimally small number, and this ratio we take a limit, then we can get the slope of this single point. Okay, so let's try that. The simple case, y equal 2x minus 4. So we know the slope already, 2, right? So if you do this, go through this, take x plus delta x, plug in, divide by delta x, and you take a limit, then you get a 2. How about quadratic equation? We put x plus delta x square minus x square over delta x, and we clean up, we get 2x. So quadratic equation, slope is initially 0, slope function is 0, and slope keep increasing at the rate of what? 2x. So quadratic equation slope keep increasing. So slope function, and by the way, slope function we put the prime, okay, the prime x, and so that means slope function of y increasing 2x. How about exponential? Okay, we put the delta x, clean up, we get the same one. This is kind of very unique function. You take exponential function and find the slope function, exactly same. So the slope of this is this value. Think about it. Okay, so finding the derivatives. Okay, here's some proof of the formula. When you have a in front of fx, and what is the slope function of this? Is a times slope function of this. So if you have a constant value multiplied to the function, that can be preserved. Okay, and also another formula here is when you add a function and take a slope function, it's going to be slope function of addition. and that is proven here. Okay, we're going too fast, but you can stop the video anytime and just digest it. Important things is it's like we call that the linear characteristic. Constant a multiplied to the function is going to be constant a multiplied to the slope function, and fx plus gx slope function is going to be slope function of the sum. Okay, differentiation practice. Now I really want to go through with you this section, but video going to be too long, so you have to stop the video and take the paper and pencil and go through this. There are 4 practice. And it's okay to finish this videos taking 2 weeks. After all, this section is going to take usually 3 months in the high school class. Okay, and another 3 months for integral, and another 3 months for series, infinite series, and so on. So the calculus is after all 1 year course, and this section is probably 1/4 of calculus, which we try to finish it in a single video. Differentiation practice, more practice. Okay, you have to do a lot of practice. Okay, and here if I cover this video is way too long. Differentiation of divided function. Okay, when you have fx gx and you want to know the slope function, then simply take a slope function of x multiplied by gx minus fx and slope function of g over gx squared, and proof is here. Probably divided function, before that we should have multiplication. The slope function of multiplication is going to be slope function fx gx plus fx and the slope function gx. So that's gonna be this. Okay, so you can try to prove this too. It's the same way you prove these, just the same method. Then you can, and this formula is extremely important for entire year of calculus. You have to remember this formula, and how you remember, don't memorize it. You solve the questions and use it. By using it, formula get into your head. Okay, don't try to remember the formula, it's useless. You have to solve practice questions, challenge questions, and to solve it you use it, and when you use it, it's getting your brain. Okay, now notation often confused. Okay, slope function, we said we just put the prime. Okay, f prime or y prime, whichever. And also we can write dy dx, we wrote it one time, or d dx fx. This is same as f prime, nothing more. Instead of prime, we just use this one. Okay, or we just write this way. This is nothing more than notation. Okay, so instead of prime, you can put the d over dx like that. The same thing, a d over dx f ax, like this. Oh, this is another good formula. Okay, when you have ax, you replace x by ax, this function, slope function, is going to be ax, like that. But ax is like, you can use u. Okay, replace the parameter. We start doing that often in calculus, replacing parameters. Oh, here you go. That's another example. When you have a function of function, okay, y equals fu, and this u is gx. So what is, when you write, this is confusing. Is this dy du or dy dx? See, that's why this simplified method sometimes doesn't tell you what it is. But if you do dy dx or dy dx, you know you are calculating a slope with respect to x or u. Okay? Anyway, dx dy can be dy du du dx. So conveniently, this is the way we can calculate slope function. You just multiply the slope function. So the dy dx is going to be fu gx, and this slope is with respect to u, not x. Okay, don't get confused. These are sometimes get confused. Now, method of taking derivatives. There is one technique called implicit differentiation. That means if function is f x y equals 0, like a conic function, then you can take derivatives and calculate y prime. Okay, here's example. Here you go, conic function. It's circle. You take a derivatives. Okay, that's needs some practice. Okay, that's called the implicit differentiation. The second derivatives, the slope of slope function. So why we care about second derivative, slope of slope? We care because I give you the reason. Okay, suppose you have a distance over time in the physics. Okay, in order to have this kind of distance that depend on velocity, the velocity is actually slope function of distance, but the velocity is a slope function of acceleration. So second derivatives is important. And actually Newton's law, ma, its acceleration equals f, is m second derivatives of distance so you apply the force according to time profile, then you will get distance function. So this is the Newton's law, second derivatives. So second derivatives is very important, and this is the section of second derivatives. In this video you learn the reason why we're talking about this and what it is, kind of things, but all practice is up to you. You pull out a lot of example practice from the math textbook and you go through that. Okay, and now minimax. Here's another reason why second derivatives is important. Okay, say you have a minimum point, so obviously you look at slope is negative, becomes 0, so slope is 0 must be minimum. Is that right? Maximum also slope becomes 0 because slope gets smaller and smaller, so slope function cannot tell it's minimum or max. You look at the second derivative, then if second derivative is positive, it's minimum. Second derivative is negative, then it's a max, right? And the saddle point, the first derivative is like this, the second derivative is still like this, it's 0, then it's a saddle point. So you can tell minimum, max, and the saddle point by looking at the second derivatives. Okay, so that's another important. Okay, well, we skip a lot of practice. You really need to go through practice and questions, and you can pull out many questions from the math textbooks and solve them all, and take some time. You can't do it in a single video, but this video, at least you get the idea of why we're talking about this and what's important, and that's the really essence of this providing this video. So I hope this video is very beneficial to you, and you can look at, if you are watching this video for reviewing calculus, the second time looking around the meaning of calculus, I hope you get deep understanding, and I hope you enjoy these videos, and I'll see you in the next video.